So let's talk about representation learning. We use deep metric learning for particle picking in Cryo-ET. Before I talk about that, I'd like to get a little bit of context, although I don't think I need to convince many of you about why I think this is important. In 2019, Torsten, a group leader in our department, published Cryolo for single particle picking. Those of you in the ML community that did the CAGO are, I'm sure, very familiar with the YOLO algorithm. And this really proved that, at least in single particle, if you can find your particle, make a little bit of training data, you can get a reliable model to pick this. Shortly thereafter, our group moved into starting to do cryo-electron tomography. And the first thing was, okay, can we apply Cryolo to tomography? And the answer was sure. For example, here on the left, you can pick ribosomes, and on the right, we can pick and trace filaments in a sarcomeric volume. But of course, this came with the caveat that you need to generate training data for every protein that you want to pick. And already then, I think Torsten had the idea that, okay, as we get into more interesting and smaller proteins, this is going to be more and more challenging, and even annotating training data for anything less than 300-400 kilodaltons becomes really, really difficult. So we wanted to come up with a strategy that would allow us to tackle these more challenging problems, as we heard about on the first day, sort of this dark matter of the cell. And our strategy for this is learning to have a general model using deep metric learning. So the basic idea here is that we have an image that's organized in real space, and we're going to apply metric learning to transform that real space and embed everything in an embedding space that is organized based on some useful feature about our data. So in this example, this useful feature would be the color and shape of these objects. What this actually looks like in tomography is that we're going to go and give it a cryo-electron tomogram, embed this tomogram in an embedding space that's organized based on shape of subvolumes, identify features or clusters in this embedding space, and use that to pick particles back in our real space. So, of course, to do this, we need a large amount of training data. This is not a self-supervised approach. This is a fully supervised learning approach, just that generalizes very well. So we went and looked through the PDB, found 100 different proteins that were structurally dissimilar, ranging in size from 42 kilodaltons to over a megadalton, calculated the cross-correlation to make sure that they weren't too similar to each other, and then simulated data very similar to what you guys have already heard about several times during the workshop. Then we have simulated tomograms where we know the real ground truth position of every particle that we can then use for deep metric learning. And our network for this is a incredibly basic 3D CNN that just takes a subvolume of a tomogram and applies some convolutional kernels, and then eventually flattens to a one-dimensional 32-length feature vector. And you can think of this feature vector as just a coordinate somewhere in a 32-dimensional space. The way we train the network is that we use triplet loss. So we feed the network triplets of data, and this is 3 subvolumes. 2 subvolumes will contain 2 different examples of the same protein, and 1 subvolume will be either a different protein or a background. And we ask the network, so we have the network with shared weights embed all 3 of these subvolumes in the embedding space, and then we calculate the dot product or the cosine distance between the 2 examples of the same protein and our anchor protein and the negative. And in our loss function, we ask the network to learn to embed different examples of the same protein close together in the embedding space, and our negative should be pushed as far away as possible. So what this looks like in practice is on the right, you can see embeddings colored by the protein identification, and you see in the beginning it's just a random mess, but through learning, the network learns not only to cluster subvolumes of one protein close together, but also to push the other proteins apart from each other, and you get this really nice clustered space. 2 things I'd like to say about this is that this is a technique that's well used in the ML community for generalization tasks, so face verification, for example. And an emergent feature of these networks is that and our hope is that if we give it now a protein that was not in the training data, based on this organized embedding space, it should embed it somewhere that we're able to cluster it, even if it's never been trained on before. The second thing I'd like to say is that a key difference between this and some of the self-supervised approaches that are now becoming quite popular is that we have 2 forces here. So in a contrastive learning self-supervised, you have a subvolume, you augment that subvolume in some way, and you ask the network to minimize the distance, the embedding space between the subvolume and the augmented subvolume. So you essentially just have your distance positive. So you get really nice tight clusters of individual proteins, but you have no force in the loss function that actually moves different proteins apart. And I do think that that will be a key feature going forward when you want to do things like unsupervised clustering in your embedding space. So we have a user interface in Nepari. We offer 2 methods of particle picking. One is where you find a few examples of your protein in the tomogram, map these in the embedding space, pick everything around it. We also have an interactive workflow where you can visualize the UMAP, the embedding space, directly on the right, and on the fly identify features of interest in the embedding space, and these voxels appear directly in the tomogram that you can then use for picking. TomoTwin's been out for about 2 years now, so we have a lot of examples where it's been useful not only in our hands, but also in the community. Also things that we never expected it to do, like picking membrane proteins, which it was never designed to do because they weren't in our training data. But I should say that we also have some cases where TomoTwin is just not working that well. And so there's certainly still some more work to do here. This slide I threw in for Tristan after the discussion yesterday to show that not only does TomoTwin generalize well to new proteins, but it also generalizes well across a range of experimental conditions. And I think this is just owing to the deep metric learning strategy that if you change your tilt range, you change your tilt step, you have a different microscope, a different detector, a different total dose. TomoTwin is able to generalize across all of these experimental conditions. So, what you guys probably care about is how TomoTwin actually does on the CZII data. And one of the questions was, did you apply TomoTwin to the competition? And the answer is yes. It was really hard not to because you guys did such a nice job in making a TomoTwin notebook that people could just run. I'd say that TomoTwin was never really probably designed for this kind of competition because in the Kaggle format, you're never going to embed 500 tomograms in 12 hours. That's a different story, but we can still run it. So the first thing I did was just have a look at the notebook, run the release model, all default parameters, what do we get out? And I was really disappointed with the performance. For example, like particularly apoferritin, I was like, I've picked apoferritin in plenty of examples. We use TomoTwin when we benchmark our new Cryos, our new detector, and it picks apoferritin no problem. So what the hell's going on here? So of course I then went and looked at the picks, and I'd say even more useful is to look at the heat map. So this you can get when you run TomoTwin locate with the right heat map. And this is essentially the network's confidence that this is apoferritin or whatever particle you're picking across the entire tomogram. And what I can see on the right, if we have another look at that, is that the network is very, very confident in locating apoferritin, and it's actually doing a very good job. But if you look at this example, or this example, or this example, we see that when you have the apoferritin particles that are really densely packed together, the TomoTwin is basically saying, yes, that is one apoferritin particle, when actually there's 7 there. So this had nothing to do with the network. You can see from the heat map that the network is actually, or the model is actually doing a really nice job, but we had a problem with our find max procedure. So the way we work is we work through this heat map, we run a find max procedure and then some non-maximum suppression to identify centered picks. And the default value of this was just simply too high because the network was so confident that these are apoferritin particles that when they're tight together, that actually the interface with 2 apoferritin particles, the network is still very confident, which is not good, but we could fix that. So by simply adjusting the threshold in our find max procedure, I was able to actually sort this out and just do a quick analysis and say that yes, okay, when we tune this, we're able to pick more densely packed particles. This might be useful for anyone that's trying to pick very densely packed particles, something you might have to play with. This is in the locate function. In the meantime, we were also working on a couple other ways to improve TomoTwin. So Torsten had been working on how we can add more training data to our network, because our general idea is that in the cases where TomoTwin we think should be picking but is not picking, it just has to be the model. The model has to be just not good enough yet. So he made an automatic scraper for the protein data bank that goes through the PDB, scans for new protein structures that meet a certain criteria that we set, for example, of the size of the protein, downloads their atomic models and makes a mole map at 10 angstroms. Then it computes the cross correlation between that structure and all the structures in our training set. And if that's below a threshold that we set, it simulates tomograms, adds this protein to our training set. So we started with the general model that's currently available, had 100 proteins that were simulated in it. Now we have 280. In the meantime, while Torsten was doing that, I went and thought, we knew when we were training TomoTwin that adding real data was very, very, very valuable to our model. That, for example, in the very beginning, it was getting confused with very dense glycogen granules that were often in cellular tomograms, really electron dense. And when I just went and picked 100 of those and added them to the training, that completely abolished that false positive. So we still do quite a lot of single particle in our lab, so I simply went to our lab meeting and said, anyone that has a single particle grid, if you have a few grid squares left over at the end of your acquisition, please let me know. I would like to take your grid, put it on our cryos, collect a few tilt series, generate some tomograms of single particle data where I know 100% the identity of the proteins that are going to be inside them, and I can annotate them and add them to our training data. So, for example, this is one of them where we have a TC toxin and actually a GRO-EL, which was carried through from purification. So I could actually add 2 proteins to the training set in this case. And I think really valuable here is that we can also have simulated GRO-EL and real GRO-EL and teach the network that it should maximize the similarity between simulated data and real data. So taking the PDB scraped new simulated data and the real training data that I added, we made a new general model that we now tested on the CZII data. So this model has never seen any of the tomograms in the CZII competition. It's never seen any of the proteins except for thyroglobulin, which was in our original simulated data set, but the rest of them it's never seen, and it's never seen any of the tomograms. And what we're able to do is actually recover pretty decent scoring. So small caveat, important caveat, this is not calculated on the entire Phantom data set because we did this just Monday or Tuesday of this week. So we just picked a subset, 20 random tomograms from the Phantom data set, calculated it there. So not one-to-one comparable with the rest of the competitors, but we were pretty happy with this score saying, okay, we don't need to train on the tomograms you guys provided. We can still get pretty decent scores out of it. Of course, if we do add the training data, we can actually improve things a little bit. And this is calculated on even fewer tomograms from the Phantom set just based on time. We'd had to do this yesterday. But adding more training data to TomoTwin does improve the picking of those particles. So of course, as we'd expect, when you're generalizing, you get a little bit worse performance than you do if you do include your data. But we're really, really happy with also the general model that we don't need to pick or don't need to train because that's what we want to do.
I think you would have won.
Yeah, should have ended.
We could, so this will not go on 500 tomograms in 12 hours. Important detail. So outlook and next steps. So we're going to make a major code and documentation update to TomoTwin. We had to add padding during the competition because the boundary models of the tomograms were really tight, and there was a lot of particles at the air-water interface or the the graphene oxide water interface that were in the first few slices of the tomogram. And initially, we weren't picking these, so we just had to add padding to our embeddings that we can now pick everything flush to the edge of a tomogram. We've also been working on some speedups. Also, Kyle has given us some speedups and code optimization that we can use. And also this FineMax tuning will add some documentation for how users can access that. Our new model with the 280 proteins plus the real data, and plus we would like to now add the CZII data to the real model. We're training and we'll make a public release so that we have an updated general model that hopefully is working better for everyone. For this, we always have the question of when we get real data, it's really valuable, and should we add it to our training set, or should we use it to measure picking performance and know whether models are better? And I think our answer for this is to choose k-fold cross-validation so that we can try to get the best of both worlds. And then, of course, the CZII data portal we're really excited about. I think there's still a little bit of work to be done there, but we'd really like to go through and see how much real data we can get out of the CZII data portal and add it to our model and just improve our model. The remaining challenges, I think the number one thing that we want to focus on is replacing this sliding window. So we typically embed on 4 A100s. That takes about 15 minutes per tomogram. People that are running on 1 GPU or on a Linux workstation, we see that it can take an hour, several hours, and that's far too slow per tomogram. So I really want to get rid of the sliding window and do something about that. We actually got some ideas from the competitors in the competition and some of the discussions over the last couple of days. So really excited about that. And I think that'll take down our sort of number one issue, which is the embedding time, so that maybe in the future we can do 500 tomograms in 12 hours. With that, I'd really like to thank you guys for your attention. I'd like to thank, of course, Torsten, our group leader in software development, who came up with the original idea and has been an incredible person to work with and work for, and a great friend as well. Yusuf, who's a PhD student that joined us, that really focused a lot on the actual competition data and training the general model for the competition data. Of course, our entire Tomo team, Stefan for supervision, funding sources, you guys for your attention, and in a shameless last minute of self-promotion, I have been with Stefan for 4 years as a postdoc, and I am starting to explore ideas for new opportunities. So if you or any in your network is interested in computational methods development, please let me know. Thank you.
Yellow and blue.
And that's exactly, of course, what we wanted from this competition, you know, to spur new developments. And I think, thanks Reza, because he contacted you and said, could you please run your TomoTwin on this? So That's really, really impressive. I have a million questions, but let's give it over to the audience.
Yeah, very nice talk. You know, I'm super excited. You know, this is TomoTwin works so well, you know, on the phantom data sets. So here, you know, it's kind of, you know, a request and also the comment. You know, you mentioned that, you know, TomoTwin is not, you know, designed, you know, for the membrane proteins. I'm still want to know that, you know, with the current form, you know, what can we do, you know, for TomoTwin to detect the membrane proteins?
Yeah,
so that's the first question. Sorry, I have a second one. Yeah. And the second one is that, you know, how TomoTwin generalize, you know, on different pixel size.
Mm-hmm. Yeah, so first question, membrane proteins. So the reason we say TomoTwin is not designed for membrane proteins is that there are no membrane proteins in the simulated data. The reason for this is that when we were first making the simulated data, we decided to use a package available temp simulator scripts, and we didn't put effort into, and there was no currently available methods of simulating realistic membranes. And so we thought, if we're not, basically the membranes in our training data are just black volumes. I think there are now more recent simulation methods that would allow you to do this, which we would need to make a training set with membrane proteins, and I think this is something we're interested in. We have seen that it can generalize to some membrane proteins, which we'd never expected. ATP synthases and some other things we're actually able to pick, but that's why we say that it's not supported. But it is something we would like to do in the future. Second question, generalization across pixel sizes. So we scale everything to 10 angstroms per pixel, and the general reason for that is that we have a very large training set from very small proteins, very big proteins. The biggest protein needs to fit in our box, and the smallest protein needs to not be one voxel in our box at the pixel size. So that's how we got to about 10 angstroms. That is a reasonable thing. If you want to pick something ribosome size or bigger, there's nothing that says you can't give it the network at 15 angstroms per pixel. And in fact, we've seen for large proteins that often helps. If you want to pick something very, very small, you can also scale it to 2, 3, 5 angstroms per pixel and give it to the network. You can pick no problem. You will generate a massive embeddings file just because the tomogram will be much larger. So that is completely supported. But by default, I would start with 10 unless you want to pick something very small or very big.
Can you just go back to your scores after improved? So
We'll start with
beta
this one.
M did badly. Is that because 10 angstroms quite a big pixel size for that teeny weeny little particle?
I think so. My intuition, and we did not test this, is that if you embedded this at 5 angstroms per pixel, you might be able to improve the performance on beta amylase. But again, not something we tested thoroughly.
Yeah. It would be great if you run it on the whole set to give us the pics, and then we can run it through the subtomo pipeline, see how they do.
I think we're absolutely interested in doing that, yeah.
I'm sure the other, there we go, thanks. Clint, you getting it? Or I'll
Yeah,
get it.
Thank you so much. That was really interesting work and exciting to see. I was wondering, after you made these model updates, did you apply it again to kind of the test data you had been looking at before the Kaggle challenge? Did it also improve performance there, or was there a risk of optimizing too much for a specific data set?
No, so we have an automatic evaluation pipeline. Every time we get a new model, we just drop it in a directory and it runs it on our entire evaluation set. So we do see nice improvements across the board.
And yeah, so I'm curious about how you did the clustering. Like, did you find new particles that were not part of the challenge? So there's like nucleosomes in there?
Yeah, we didn't. So I wanted to, but never had time to run clustering on the CZII data. So this was all reference-based. We went through TS999 and just extracted every annotated subvolume and tried all of them as references and see which one worked best across the phantom data set. I would like to, my idea was, okay, we'll first do that and then do the clustering, and we just didn't get a chance yet.
Cool, thank you.
There we go. Sorry, coming to you, Gus.
There I go.
I've got it. You do that side, thanks.
So just two kind of specialist questions, maybe. One, what's the dimensionality of your embedding space? And second, if you ran your, how long, you say you can't run in 12 hours, how long would it take if you ran what you have right now on the whole thing?
Yeah, so 32-dimensional embedding space. We played around, I think initially it was 128 dimensions, and we found that increasing the dimensionality did not improve the performance, and so we basically decreased it as much as we could before we started to see a decrease in performance. And we landed at 32. Second question, sorry.
The second question is,
how long?
if you ran it, how long would it take?
Yeah, we at the Max Planck Society have access to a very powerful computer where it takes about 15 minutes per tomogram on 4 A100s. Depends how long you have to sit in the queue for those, but we're able to do 20 tomograms overnight on it.
Yeah, so the 500 tomogram set
Might take a week
for
or
the
two.
challenge would still be like a really heavy lift.
Yeah,
Yeah.
yeah, and I think that's the number one thing that I have sights on that we need to improve.
Great. Thank you.
Yeah.
Well, maybe Walter can comment, or somebody can comment. Do the math for me. I mean, you have the A100s, you used whatever, so his 15 minutes times 500.
6 hours per tomogram on the T100s.
Ouch. Okay, so that's tough. Yeah, but okay.
I think with masking, I was able to get it down to 300 or 400 with masking the tomograms before embedding them. Yeah.
There you go.
Yeah, it's two things, right? It's the computational speed, but it's also the memory requirements, and I'm sure that's a huge issue as well. So,
Yeah.
Yeah, very impressive. Marvelous improvements. Just, very, very exciting. You mentioned something, if I heard you right, in terms of wanting to be able to then change the embedding so that, real things were separated further in the embedding space. What are the strategies for doing that, and what would be the consequences you go to, hundreds of, items in your training set?
I want to make sure I understand the question. So
Maybe I didn't understand the question either.
no, that's okay. So I think an important detail about this approach with triplet is that you have always a negative, and this forces distance during the learning between different proteins. And I think that's a key difference between self-supervised contrastive learning that you don't have. And I think that will be important. Well, we're able to do unsupervised clustering just based on densities in the embedding space, and my intuition tells me that that's not going to work as well on self-supervised learning because you don't enforce that distance between different proteins. I don't know. I've been surprised before, and I'd be happy to be surprised again because I think the unsupervised approaches also really are really, really cool.
Have you tried embedding the same protein but in a different conformational state, and can TomoTwin actually distinguish different conformational states?
So that we haven't. We've never tried. I've never seen, like when picking ribosomes, clusters for different sets of ribosomes. And I think because we have all the training at 10 angstroms per pixel, that if you wouldn't expect a large shape difference at that resolution, I wouldn't expect TomoTwin to pick that or pick up on that. Yeah.
Just a quick one to follow up on that. Will it distinguish between 60S and 80S?
Yes, so 60S and 80S and 70S and 40S are all in the training data. Yeah.
Why did it do worse on beta-gal than thyroglobulin, which are...
I think that's because thyroglobulin is in our original simulated data set. Yeah.
Got it, yeah.
So even the model that's publicly available at the moment, I think did better on thyroglobulin than like apple ferritin, which was weird. Yeah.
So when will it be available? Because we'd love to try it on ATPase. You said it works even though it's not membrane trained.
Yeah, so I mean, we could release this model today, but I would really like to do the k-fold cross-validation because at the moment it's not making use of the CZII data. So I think we need a month or so to set that up and make sure that it's really running. The training doesn't take really long anymore. Actually, we can train in a complete TomoTwin model in a few hours now. We have a new training strategy. It used to take a week or so. But we need some time just to set up that k-fold cross-validation because I think that will be important, and I don't want to release a model now and then in 3 weeks release another model.
We'd be happy to be beta testers. Yeah.
Yeah. You train it on, say, the winners, where they didn't have as many false dismissals?
Yeah, so if you have updated annotations, we train on extracted subvolumes. We don't train on tomograms. So an interesting feature about this is when I go for real data, I don't need to worry about false negatives because the network will never see them. It only extracts and trains on things that I pick. So if there are false positives, that would be bad, but false negatives are not important.
The data set that you're training, is that also going to be made available?
Yeah, so it's our original data set's on Zenodo, and we're certainly planning to release the next one on Zenodo as well. So yeah, all our code's open source. We're happy to release everything that way.
Thanks.
One over there.
Have you ever looked into whether the encodings encode any meaning? If like different dimensions in the encoding, if you vary the parameter there, whether
I played around with this a little bit. That I tried to sort of visualize also the latent space after different convolutions. And to be honest, I had a hard time visualizing 3D latent space in a meaningful way. It's a good idea. I would like to do it. Maybe I'm just not a good enough software engineer to do it. Yeah.
Any one last question? I just want to comment that I saw Adam Frost give a talk at Keystone last week, and he had quite a nice membrane model. So maybe there are some that you could try. Yeah.
I think it is possible now. We were also discussing last week in a meeting that I think there are some more recent tools that would allow us to do that. It just simply requires.
Yeah, there's a question online. Okay. This is one from Michael Smith. Are all the negatives explored for each identical pair?
I'm not sure.
Are all they? Yeah.
Are all negatives? So we use online triplet mining. So we categorize the triplets between easy, semi-hard, and hard triplets depending on essentially how difficult it is for the network to tell the difference between the two. And we do use an online triplet mining strategy that favors certain triplet pairings because they are more useful in training the network and allow you to train faster than exploring all triplets, most of which may not be useful.
Any others online? Okay. All right, that was marvelous. I really thank all the speakers at this meeting who have kept to their time and allowed plenty of time for questions. So, often at meetings, people just exceed their time and it's like, oh, there's no time for questions, rush on. So this has been really a lovely discussion and question time. Thanks, Gavin.